Should we start now? Yeah, cool. So today I'm gonna talk about the emerging memory technologies. And firstly, please allow me to introduce myself. My name is Haiyu Mao, and I'm currently a postdoc researcher at Safari. And my research interests includes computer architecture, algorithm, and architecture core design, processing in memory, especially focused on the non-volatile memory side, and processing storage, bioinformatics, and machine learning acceleration. And at the same time, I'm also a group associate at the ETH Future Computing Laboratory, which we cooperate with industry and mainly the cooperating on different topics and computer architecture side. And there's more information on my homepage. If you're interested, you can take a look at the details. Okay, so so far we talk about the memory technologies such as DRAM and flash memory, but they are based on the charge-based memory. And for the charge-based memory, at some point, it's very hard to scale because the cell size is becoming smaller and smaller, and it's very hard to design good sense amplifiers to identify the levels of the electrons stored in the capacity, for example, in the DRAM, and to sense the floating gate, the data stored in the floating gate in the flash. So here are the two examples of flash and DRAM. They use the floating gate charge and the capacitor charge to store the data and read the data. So to overcome the shortcomings, there have been a lot of work in this area, such as memory-centric system design and novel memory architectures interfaces and the functions. And the key issues that now are trying to focus on this area can be enable the reliability at a low cost to provide some higher capacity and to reduce the energy, reduce the latency, improve the bandwidth, and reduce the waste such as capacity waste, bandwidth waste, and latency waste, enabling the computation close to data. These are the current efforts spent on the how can we make a trade-off between the capacity and the performance. And here are the papers. There are many works done in this area to reduce the capacity at the same time to ensure the performance and the accuracy. Then it comes to another side, like that focusing on the charge-based memory. There's another solution called the emerging resistive memory technologies. It can be more scalable compared to DRAM, since they are non-volatile. They're based on different technologies, not the charge-based memory. It's instead of charging and drain the electrons stored in the capacitor, NVM, they usually use the resistance to represent the data stored in them. And here is an example of phase change memory. The data is stored by the changing the phase of the material here. And the data can also read by the detecting the material's resistance. And this kind of technology can be expected to scale to the very small technology size. And there's a prototype in the 20 nanometers in 2018 by IBM. And it is expected to be denser compared to DRAM, which means that you can store more and more data inside the memory with the smaller size. So, however, there's many challenges in this emerging non-volatile memory technologies. I will talk about the details in later slides. And there can be we need to consider about how to overcome these challenges to make them they can be kind of like either replace the DRAM or think about it can be worked together with DRAM or can be like heterogeneous memory system. And here are the papers that focus on the emergent technologies area, and some papers are solving the challenges such as writing power. Writing power usually is really high in the NVM compared to the writes to the DRAM. And here is an example that Intel often persistent memory, and it's a very interesting story since it can provide a lot of benefits. So there's a lot of researchers doing such a analysis on this, how can we utilize this non-volatile characteristics to enable good performance inside the whole memory system. However, it also causes a lot of problems, such as when we consider there's a persistent memory, we need to consider about the consistency when we store the memory, when we write the memory. So this company, they decided to stop this business at I think it's around 2020. And it's not because this kind of technology is not convincing. It's just because they consider to the financial cost and compared to the traditional DRAM, maybe. But there's many opportunities here. And here's a paper that our group did in the architecture in the phase-changing memory as a scalable DRAM architecture. And here's another paper that the phase-changing memory and the future memory. And so let's compare about the charge-based memory and the resistive memory. So charge-based memory, for example, has a DRAM and flash memory. We can write the data by capturing the charge and read the data by detecting the voltage. And resistive memory, which I mentioned before, it works in a very different way compared to the charge-based memory, which we write the data by pausing the current DQ and read the data by detecting the resistance that to represent the values inside the NVM. And there are some promising RAM resistive memory technologies such as PCM, STM RAM, and memory source such as RAM. These are the similar things, but they write in different names. And I firstly talk about the PCM and the STM RAM to compare, to give you more hints about how this new technology can be used in the current memory systems. So PCM, it works by injecting the current to change the material phase, and the resistance is determined by the phase. And STM work similar way, like injecting the current to change the magnetic polarity, and resistance determined by the polarity. And memory source, it works similar, like injected the current to change the atomic structure of the material, and the resistance is also determined by the atom distance. So let's firstly talk more details about the PCM. And here is the cell structure of the PCM. So it has two stators in the physical way. So this can represent the low optical reflexivity and higher electrical sensitivity. And the other one, it represents the low electrical sensitivity. So you can use these two states to represent the logic 0 and 1 in this memory. But there's also studies to divided these states into multiple status by the range of the resistance levels. So we can store small bit other than 0 and 1, which is high resistance and the low resistance in this case. And the PCM cell can be switched between the status, reliability, and quickly. Quickly is a relative way. It's not compared to DRAM. The write to the PCM, they usually is much slower compared to DRAM. And so let's have a look at how to write a PCM cell. So it through the change the phase and current injection, we can do the two options. There are two options. One is set and one is reset. So through set, it can sustain the current to hit the cell above some threshold. So you can do the write, and through reset, the cell hit it above the timeout and to change to another state. And the read is just detect the phase and the material resistance to check its logic 0 or logic 1. And here's a picture of the set state. And here's another picture about the reset state. And you can compare that this part. You can see the difference of the resistance, and the set is usually represent a low resistance, and the reset is represent the high resistance. You can either use it to repair the 0 or 1 or 1 or 0. So encoding about the physics to the logic mapping. And so what are the advantages of PCM? So it scales much better compared to DRAM and flash because it requires the current puzzle, which scaled linearly with the feature size, and expected to scale to 9 nanometers in 2022, and which can prototype to 20 nanometers, which is smaller than the DRAM. And it can also be denser than DRAM because it can stop multiple bits due to the large resistance range. Let's recall about the charge-based DRAM. They use the electrons stored in the capacitor, and they use the sensing methodology to detect to read the data. However, here you just use a very large range of the resistance to store the data, and to read the data can reduce the disturbance. That's why it can scale better compared to the DRAM. And also it provides a non-volatile ability, which can retain data for more than 10 years, which means once the machine is turned off, I don't need to write the data in the DRAM to the storage. I can just immediately turn off the machine. And also it doesn't require any refresh, since the DRAM need a refresh to retain the electrons in the capacitors. So it requires low idle power. When you store the data is there. You don't need to extra energy to handle the erroneous inside it. And okay, here is the more detailed example about how we use the PCM cell. Here is a cell resistance. As I mentioned, it's a very large range, and you have a reference for the resistance. And it's smaller than, if it's smaller than the reference, then it's identified as logic 1, and it's larger than the reference, then it's identified as 0. So if you look at the multiple cell PCM, that we can divide it by the resistance range to multiple ranges. And so we can store 2 bits into the in the single PCM cell, that we use this range to represent 1, 1, and this the second range to represent 1, 0, 0, 1, or 0, 0. But this has some, yeah. Yes.
Is this a limitation on how much?
Yeah, yeah, it's a really good question. So the major disadvantage of this kind of non-volatile memory, the big problem is the endurance problem. That means that you can, when you frequently change the status between different phases, then sometimes it cannot be changed anymore. Or sometimes it can only, for example, at the beginning, the range of the resistance you can change is this large. But through when you write it very often, the range will shrink. And until one point, it cannot be changed anymore. So there's some reliability issues for the endurance problem in NVM, and it's a very big challenge when you're using NVM. I will talk about more details about this later. Yeah, that's a really good one. Cool. And once you use the multiple level cell NVM, you can store multiple bits, that's true. But also, once you divide it into multiple ranges, it means that you have a higher possibility to for the disturbance. For example, if I have a resistance close here, the reference close the reference line, then it may be not properly sensed as a correct value when we divide it to multiple resistance ranges. Okay. So this means that when you have a multiple level cell, you need a more precise sensing scheme and the modification of the cell contents. And also you need a higher latency energy for the read and write. So here is there's a survey paper in our group to survey all of the NVM memories, and you can take a look to compare what's the difference between them. There's many parameters and a lot of mechanisms used in different phase change memories as a scalable DRAM alternative. And here's a table summarize all of the existing PCM technology. As you can see, we don't have a really good standard for what should be reported in this area. And the paper, sometimes it's not very clear according to the different parameters that are used in these NVM technologies. But there's some good study that, as you can see in the last column here, they have a lot of detailed parameters. But the one thing that I want to mention here is that there are many choices inside when you design the single NVM devices as a memory, such as the voltages, power, the ranges that you use, how do you divide these ranges, and how do you use the reference for this resistance range. And so let's think about that. We have a new PCM, we have a new NVM technology. How can we use it in the current memory hierarchy? And now the current memory hierarchy, we use caches. Usually it's SRAM, and memory is usually DRAM, and storage usually use SSD or HDD. Sorry. And all of the parameters showing for the characteristics showing in the non-volatile memory is more close to the main memory side, as the accessing latency is close to DRAM, but it's a little bit slower than DRAM, but it's much faster compared to the flash memory compared to the storage side. So it's usually considered PCM as a main memory, but we need to overcome many challenges. And as you can see here, there's the details about the when you compare the read latency, write latency. and the write bandwidth compared to the DRAM. And especially the write latency, it's slower, much slower compared to DRAM. And here are more comparison, the data about the dynamic energy that you need to use in the DRAM compared to the non-flash. And the endurance is a very big problem here. So basically for DRAM, we can usually write as much as possible nowadays. But for the phase change memory, it's much lower than the DRAM, but it's still better compared to non-flash memory. And the cell size, which is a big advantage of the NVM-based NVM technologies, it's much smaller compared to DRAM and non-flash memory, and with a very good scalability, because you can also consider to store multiple bits in one cell. And here are the overview of the pros of DRAM, which is better technology scaling and provides some non-volatile abilities, which means that you can store the data persistently inside the memory. And we also have the low idle power compared to DRAM. We don't need to do the refresh operation. And the downsides is like it has higher latency when you access the NVM, emergent NVM, especially for the writes. And also there's a higher active energy compared to DRAM. And the endurance is very low compared to DRAM. And reliability, there are some also reliability issues, such as the resistance may shift, and when you divide it by the resistance range, divided by many multiple ranges to store multiple bits, then it may be a bigger reliability issue in the multiple level cell. And however, the change is enabling the PCM as main memory, and to mitigate the PCM shortcomings and to find the right way to place the PCM in the system. So when we make a trade-off between these pros and cons, then we can find a good way to use the PCM. And here is an example that how when we have this kind of PCM, how we should we consider replace, for example, replace half of the DRAM. We use both DRAM and PCM connected to the memory controller, and or we think about replacing all of the DRAM in the system. And here is the middle one, usually called a hybrid PCM and DRAM memory system. But we need to consider that how to partition and mitigate data, migrate data between the PCM and the DRAM, and how to redesign the, for example, if we consider to replace all of the DRAM with PCM, then we need to consider how to redesign the entire hierarchy, and also how to redesign the cores to overcome the PCM shortcomings. And here's a paper that proposed how to using the phase change memory as the scalable DRAM architecture. And here, as you can see, the parameters used in this paper, the latency is lower than the DRAM, and the endurance is a problem, and energy, consider the energy is also a problem in the write energy is also a problem in compared to DRAM. So here is the results that when you consider to replace DRAM with the PCM in a 4-core and 4 megabyte L2 system. And the PCM is organized as same as DRAM. which is we have row buffers, we have the banks, and we have some peripheral circuits to support the read and write. And if we directly use the organization of DRAM for the PCM, we observe 1.6 delay and 2.2 energy consumption. And also it's very soon like dies for the PCM. It's because that we didn't consider this architecture for DRAM. We just used the architecture designed for, we didn't consider the architecture for PCM. We just directly use the architecture that they designed for DRAM. But sometimes there are some characteristics such as we don't need in the NVM because they are quite different technologies. And so what we don't need here for the PCM is that for the DRAM, we need the array sensors for the array cells in the row. But for the PCM, we don't really need that. And so if we consider to remove remove that sensor amplifier part, and we can have more spaces to use multiple narrow row buffers in the PCM chip. So then we can reduce the array reads and writes and to achieve better performance, to reduce the endurance, reduce the endurance problem, and also save the energy. So the idea here is to write into array at the catch block or word granularity to reduce the unnecessary will that we propose narrow row buffer in the PCM compared to DRAM. So the results showing here, as you can see, compared to we directly use the architecture for DRAM. We design the architecture for PCM, then we can achieve better performance, and also the energy consumption is almost close to the DRAM, and also the endurance is can be improved a lot in this case. And so the takeaway is that the worst case lifetime is much shorter, and the problem is that the worst case lifetime is much shorter, and in sensitive applications see the large performance and energy. And there's some can be optimistic PCM parameters to enable the we leverage the benefits of the PCM. And here is details about the paper. And if you're interested in more details, then you can take a look at this paper. Here's another paper about the phase change memory and to use as a future memory. I think there's some repeat. Sorry for this mistake. It's the same as the previous one. And let me see. Yeah. So then let me talk a little bit more about when we use the multi-level cell. So when we divided the range of resistance in the PCM cells, and we want to use that as a multi-level cell, it requires at the same time the sensing time is longer for a bit, for a cell, because we need to sense two bits, one the most significant bit and the less significant bit here. And also we only determine the one bit and before the other bit. So we have some observations in when we accessing the PCM cells, which is read memory, and which means that the read latency and energy of bit 1 is lower than that of bit 0, because recall that we have different states for the physics side to represent bit 1 and bit 0. And also it's due to like how PCM cells are read. And this is one way that PCM, to read the PCM cell, we have a capacitor to fill the reference voltage. And we connected the reference voltage to the PCM cell. So we did evaluate how long the electrons will be drained out. And this is a infer data value to read the PCM cell. And so here, as you can see, when we divide it into 4 ranges, when we have the initial voltage, which is full charge capacitor, we detect the voltages inside the cell, and to determine which are the status stored in the cell by seeing the voltages drained over the time. Okay. So in the existing device, the most MLC bits are read at the same time, but they need to wait for the maximum time to read both bits because some, for example, you read 0, much faster than the 1, but you still need to wait until the longest cell to be read at the end. So, however, we can infer information about bit 1 before this time. And for example, here, the bit 1, the first most significant bit is bit 1 or bit 0. We can use this time reference to determine bit 1's value is which one, and also use another reference to determine the bit 0's value is which one to which one. Okay, here is the map of the status of when you write the cells. As you can see, there's 4 states, and the different they have different like write latency when we consider about the status transfer in these 4 states. And there are more analysis in this paper, and if you're interested in the details, you can take a look at this paper. So far, do you have any questions so far? Okay. Now continue with STT-RAM as the memory. That's all about I want to discuss with you about the PCM. And another technology is called the STT-RAM. Let me check the. Here is the cell structure of the STT-MRAM, and it's called the magnetic tunnel junction device, which has a reference layer, which has the, here is the reference layer with the fixed magnetic orientation, and the free layer, which can be programmed to either parallel to the reference layer or the anti-parallel compared to the reference layer to decide the stored is logic 1 or logic 0. And magnetic orientations of these free layer determines the logic states of the device, which is high resistance or low resistance. And for the write and read, for the write, we push large current through the MTJ cell to change the orientations of the free layer. And for the read, we just sense the current flow of the resistance level of this cell. And the cell of the STT-RAM is structured like this way, and it's larger compared to the PCM and RM, other MEM cells, as it's required large MTJ cell size, also the access the transistor to control the connected to the word line bit line. So here is the summarization of the pros and cons of compared to DRAM. So the advantages is like similar to that PCM, which is better technology scaling and which provides a non-volatile ability, and also has low idle power compared to DRAM. And the downsides is like also similar, but It has a higher write latency, higher write energy, and poor density. This is one different compared to the PCM, since PCM has a higher density compared to the DRAM, but the STT memory has a poor density. Currently is poor. And also some reliability issues in this kind of NVM technologies. But we can provide another level of freedom that we can make a trade-off between non-volatile for lower write resistant energy by reducing the size of the MTG cell. And here is a paper that we demonstrate the architect the STT-MRAM as the main memory, and we demonstrate in do some experiments on the 4-core 4 GB main memory multi-programmed workloads, which provides a similar performance compared to the DRAM, but it's less energy savings compared to DRAM. And here's a paper with describe STT-RAM as energy efficient memory alternative. And let me check the time, and we can continue. Maybe continue a little bit more, then we take a break. So there's another interesting topic is hybrid memory. When we consider, okay, we have emergent non-volatile memory now, and we have traditional DRAM, and maybe we have some other characteristics of the emergent non-volatile memory devices different in NVMs, let's say. So we can consider the architecture like this, a hybrid memory system that we have the CPU and we have a memory controller for DRAM and a memory controller for PCM, where the DRAM is fast and durable but small, and it has some leakage and volatile with a lot higher cost compared to phase change memory. Phase change memory on the other side is larger compared to DRAM and provide non-volatility, and also the cost is low. But however, the PCM is slow and it's very easy to be worn out. Also, it has high active energy. So we then need to consider, once we have these two different devices in the memory system, how can we use the hardware and software design to manage the data? For example, we have application with some data that is quite large, but it's not very often used. Then we can consider them to store in the PCM, since the density of PCM is very high, but the performance is relatively slower than the DRAM. So we need to consider that how we can do this design to manage the data allocation and movements to achieve the best of the multiple technologies, to utilize the advantages of different technologies here. And so there's challenges and opportunities to providing the best of the multiple metrics with multiple memory technologies. And also when we consider about this kind of things, there's we can do a heterogeneous, configurable, and programmable memory system. So when we consider such as high hybrid memory system, there are some issues that is listed here. We should consider it as a cache or the main memory, and we should consider about the granularity of data move and management. It's a fine-grained granularity or cross-grained granularity. And also the hardware and software cooperative to manage data, place the data, and migrate the data, and also when to migrate the data, and how to design a scalable and efficient large cache to make the system benefit from their performance. And there's one opportunity that we can use the DRAM as a cache for PCM. So PCM is a memory, DRAM is also memory, but it's used as cache of the memory. And the benefits can, so is obvious here, we can reduce the latency on DRAM cache hits and the write filtering. So we can reduce the writes to the PCM, since the writes to PCM is consumes high energy, long latency, and also at the same time, it will cause some endurance problems. And the memory controller and how we'll manage to manage the DRAM cache, which can eliminate the system software overhead. And there are three issues here. We need to think about what data should be placed in the DRAM versus kept in PCM. And also what's the granularity of the data movement? Because sometimes when you move a very large data, it can cause a lot of overhead inside the memory system. And how to design a low-cost hardware management DRAM cache. And there's two directions that can address these issues. One is locality aware data placement, and another is chip tech stores and dynamic granularity. And we will talk about these papers later. Should we take a break now? Maybe it's a good point to take a break. Is it tuning? Good. Okay, then we can continue. So here is the system that we use DRAM as a cache for PCM. So the goal is to achieve the best for both DRAM and PCM or NVM, let's say. And we need to minimize the amount of DRAM without sacrificing the performance and the endurance. And DRAM as a cache to tolerate the PCM latency and the write bandwidth. And PCM as a memory to provide a large capacity at a good cost and power. So as you can see here, so we store the text and the data in the DRAM buffer, and when we write to PCM, we connect through this kind of structure. And so then we can consider about the lazy write to using the DRAM as a filter to, for example, the page from the disk installed only in DRAM, not PCM, and partial writes, which we only write the dirty lines from DRAM pages when we write the data back to the persistence memory. And also the page bypass, which we can discard the page with full reuse on DRAM eviction. And here is the result when we simulate on a 16-core system with 8 GB DRAM memory at this configuration. And the assumption is that the PCM is 4 times denser compared to DRAM, but it's also 4 times slower compared to DRAM. So this is done by the simulation, and you can adjust the parameters to see the benefits and to see how you can guide the configuration between the DRAM size and the PCM size. So also the DRAM block size is same as PCM block size used in these experiments. So as you can see here, for the 32 GB PCM plus 1 GB DRAM, which is using the DRAM as the cache of the PCM, it can achieve almost like a similar comparable performance compared to we use the pure DRAM. But recall that the DRAM cost and the power is more costly compared to the PCM, right? So through using the DRAM as a cache for the hybrid memory system, we can like replace the pure DRAM here. But if we consider about only use the PCM, then a lot of problems like writing problems, long write latency and long write energy, large write energy to PCM, it will hurt the system a lot, as showing here in the blue bar. So it's better that we use the PCM mainly, but we use the DRAM as a cache. So here's a result of the PCM DRAM hybrid performance similarity to the similar size of the DRAM, and there's significant energy savings within the PCM and DRAM hybrid. And the average lifetime can be very long, to like nearly 10 years, which is very good. Let me see the here, as you can see, the hybrid memory compared to the pure DRAM, and small pure DRAM and large pure DRAM can achieve the good trade-off between these two. So there's more details in the paper listed here, and if you want to know more details, you can go to have a look at this paper. And another thing that we consider in this kind of memory, hybrid memory, is that okay, let's assume that we have an application that with a lot of data access to the memory. Then we have the memory controllers connected to the memory A, which is a really fast and small memory, and the memory B, which is large but slow memory. This is a generalized situation for the hybrid memory system. It's not doesn't require to only DRAM and NVM. It can be also to different NVM technologies, and can also be to different DRAM technologies. And we want to utilize the fast memory as much as possible to benefit from the performance, right? Then we to migrate the pages in the slow memory to the fast memory if it's accessed very frequently. And then we need to decide which memory do we place each page in, and to maximize the system performance. However, when we want to utilize the memory A as much as possible, there can be reduced. There can cause a lot of pages stored in the memory and accessed very frequently. So it can be a bottleneck here for the memory A. However, at the same time, even though memory B is slower compared to memory A, but memory B is idle here. And then we need to, at some point, when the memory A is overwhelmed, then we need to consider about how to make a trade-off between these access to the memory, fast memory and the slow memory. So the load should be balanced on both channels. Consider about the bandwidth, so different bandwidths of the different memory units. And the page migrations have performance and energy overhead. We need to consider about that when we think about the page migrations between these two different memories. And so here's the idea that we can characterize the data access patterns and guide the data placement in the hybrid memory when we run a program. And for example, the stream access, since it's doesn't make too much difference between the PCM and the DRAM, so we can use both. And the random access is on the other side, since it's much faster in DRAM, but it's slower in the PCM. So we want to do, the key idea is I want to play the random access data with some reuse in the DRAM and the streaming data in PCM. And the key observations and the ideas here is to use the since the row buffers exist in both DRAM and PCM, so we can, however, the row hit latency is similar in DRAM PCM, but the row miss latency, which in DRAM is much smaller compared to the PCM row miss latency. So we consider to place the data in DRAM, which the data is likely to miss row buffer since the DRAM has lower row buffer penalty, miss penalty. And the data should be reused many times since the cache can only was the movement cost and the DRAM space. So here is the result when we consider about this kind of optimizations. And as you can see here, the design of this system can make a really good trade-off between the pure PCM and the pure DRAM. And here is a paper, and you can have a look at the details if you're kind of interested in this topic. There are some weakness in the existing solutions for all of these hybrid memory, since they are all heuristic that consider only a limited part of the memory access behavior. For example, before we only consider about the write is fast or not, the access to the memory is fast or not, but we didn't consider other aspects. And it cannot directly capture the overall system performance impact of the data placement decisions. So it can make some local optimization decisions currently, but maybe like it's not optimized in the globally. So this is an example here that we have a lot of memory parallelism in the memory system, and the number of concurrent memory accesses from the same application when the page is accessed, and affects how much page migration help the performance. Here is an example. We have the page one to access the memory, the slow memory, and we have after migration of this page one, we can achieve some cycles reduced. However, when we consider there's a memory parallelism that we have a lot of concurrent access to the memories, there's page 2 and page 3 access the memory B. If we only migrate the one page to the system memory A, we still need to wait for the memory B to access to be finished. So you must to migrate the 2 pages to reduce the store time. And because migrating the 1 page alone cannot be helped in this case. And so we conclude that the page migration decisions need to consider the memory level parallelism in the system. So the generalized mechanism is that we can directly estimate the performance benefit of migrating the page between any 2 types of memory, and places only the performance critical data in the fast memory. And here is details about this paper that memory manager can work for any hybrid memory, for example, the DRAM with the NVM or the DRAM with the IO DRAM. And the key idea is for each page, use comprehensive characteristics to calculate and estimate the utility, which is the performance impact of the migrating the page from one memory to the other in the system. and migrate only the pages with the highest utility, which means that the page can improve the system performance a lot when it be migrated to another memory unit. So these are some key technologies for each page. We estimate the utility using the performance model, and migrate only pages which whose utility exceeds the migration threshold from the slow memory to the fast memory. And also we need to judge this threshold, adjust this threshold dynamically to provide the timely feedback to the memory system. And there's more details about how we can estimate the utility as a performance using a performance model. For example, the application store time reduction we need to consider about. It's like consider how much would migrating a page benefit the performance of the application that the page belongs to. And another thing that we need to consider about is application performance sensitivity, which we consider how much does the improvement of a single application's performance increase the overall, the entire system performance. So these are the mechanisms using when we decide to migrate the page or not. And here is a result about this paper, this mechanism, the idea. And as you can see, it has a lot of speed up compared to the state-of-art hybrid memory manager at that time. And we also test some sensitivity for this technique in which we adjust the values parameters in the slow memory to see if we can still benefit a lot from this manager, and the answer is yes. So this improves the system performance from a wide variety of hybrid memory systems. And here is a paper, and it's a very interesting one. If you want to know more about the details of this mechanism, you can take a look at this paper. And so, as I mentioned before, there's challenges, but there's also opportunities. And we need to enable emergent technology, how to augment the DRAM, and to how to manage the hybrid memory system to provide the most benefit for performance benefit and capacity benefit at the same time. And therefore, we need to design think about designing the effective large DRAM caches. This is another another interesting topic that we consider the DRAM as a large cache, and but a large DRAM cache also requires a large metadata usage in the, for example, the tag and the block-based information stores in the memory. And how do we design an effective DRAM cache? Now, when we want to access the data, CPU send a load instruction to the memory controller, and it has a metadata here, and we access the data from the DRAM. It has the metadata stored on the chip in the memory controller. And we access the data from the DRAM, and then it's finish the load X instruction in the current system. But then there's another solution that we can store the text in the same row as the data in the DRAM, so that we can store the metadata in the same row as the data, and the data and metadata can be accessed together. It can reduce the text storage overhead on chip, and however, it causes some downsides. For example, the cache hit is determined only after the DRAM access, and the cache hit requires 2 DRAM accesses. And the other idea is that we can, the first idea is store all of the metadata in DRAM to reduce the metadata storage overhead. And the other idea is we can cache on-chip SRAM frequently access the metadata, which only cache the small amount to keep the SRAM size small. And the other one, the third idea is we dynamically decide the data transfer granularity to cache. Since some applications benefit from caching more data, they have good spatial locality. However, there are some other applications that can not benefit from caching a lot of data, that they have large granularity with the bandwidth to reduce the cache utilization. So the key idea here is to simple dynamic caching the granularity policy that different applications can benefit. Is to then to provide a cost-effective analysis to determine the best DRAM cache size and group size, and group many memory into the sets of rows, and different sampled rows follows different fixed caching granularities, and the rest of memory just follow the best granularity to get the cost benefits, which we make the trade-off between the access latency and the numbers of data that we want to catch on the on chip, and also perform every content. Okay. Here is a result about this idea that we can reduce the channel contention and improve the spatial locality. Also, there's fewer migrations, reduce the transmitted data and channel contention. And there's more details in the paper, and you can take a look at the details inside it. Let me check. Okay, so here is a paper to summarize there's many design choices and design parameters that we need to consider about when we design the different state-of-art DRAM cache as in the main memory. For example, you can consider about how large is the data to be migrated each time, and we can consider how the cache line size and the different software or hardware manage the mechanisms and a lot of other things, and we need to play with and make a trade-off to provide a higher performance and lower cost in the memory system, hybrid memory system. I think it's a good time to take a break, and then we back in 10 minutes. Let's get started. And here is another paper that focuses on tackles the problem that we use the cache, use a TLB, and to store the page table. There's no tag stored in the needed for the DRAM side, and can enable the new lightweight lazy TLB coherence protocol. And there's a new bandwidth aware frequency based reference policy used in this paper. And here's the paper. And there are many other opportunities provided by the processing, provided by the emerging memory technologies. And one thing here is, for example, the merging the memory and the storage, and new applications considering the emerging memory technology, and more robust system design and processing tightly coupled with memory. And I firstly share with you my experience about the processing using memory, which is the fourth point here, which tightly couple the memory with the processing units using the non-volatile memory to do the computation in situ. And recall we have the processing using memory for the DRAM side, which we use the DRAM cells to do some bulk bitwise operations, and which can provide a really good performance compared to we load the data to the processing units and then do the processor data at the processing unit, and you write it back to the DRAM. Instead of that, we directly using the DRAM cells to involved in the bulk bitwise operations. And thus, since we talked about the non-volatile memories, there are more opportunities involved in this area. Since non-volatile memories is more reliable, they use the resistance to store the data, and we can do more operations, enable more operations with the physical side, that we consider the relationship between the voltages and the resistance stored used in the NVM cells. So this is the example that I think you may learn from the previous lectures, that we have a fast bulk bitwise and/or operation support in DRAM. And the ambit is another very interesting paper that using the in-memory exciter for the bulk bitwise operations. And here's another paper about the in-DRAM bulk bitwise execution engine. And also the SIMD-RAM, which is a framework to for the bit serial single instruction multiple data processing using DRAM. And those are courses if you're interested in, can look at the more details in these courses about the processing using memory. And also another course about processing using memory in the previous years. And the thing is that, okay, we know that we have the DRAM that can do some bulk bitwise operations. And now we have the NVM, which use a larger resistance range to store the data. And of course, we can use it to support the computation at the same time with more abilities compared to DRAM. Here is an example that we used NVM to do the bulk bitwise operations. Previously, if you consider the traditional approach, that we have the CPU here, and once we need to do the computation on data, then we need firstly read the data to the CPU and do the computation. Then we store the data back to the memory, NVM-based memory. But this kind of like approach, when there's a lot of data being computed at the same time, also we require only the very single computation, a very easy computation on the data. We need to read and write the data to NVM many times, but it's very inefficient for the NVM system. So what is proposed here is like very similar to the n-bit thing, that we don't involve the CPU in this computation, and we modify the sense amplifier, which is already existing in the NVM banks, and we directly load these two rows in the NVM to use the modified sense amplifier to do the computation and store the result in the NVM. So by doing this, we can firstly reduce the data movement between the processors and the memory system. Second, we can also enable the internal high bandwidth of the computation. So another thing that makes me super excited about the NVM processing using NVM cells is the in-memory crossbar array operations. That we have, for the NVM arrays, we have the crossbar structures such as memory source, RAM, phase-change memory, IEDM RAM, which the crossbar arrays can be used to perform the dot product operations using the analog computation ability, and can operate on multiple pieces of data using the Kirchhoff's law. And the bitwise current is the sum of the product of word line, and computation is in analog domain inside the crossbar array. But it needs preferred circuits for the digital to analog conversion, and also analog to digital conversion for the input and output data. So let me talk about more detail about this technology. So here is an example that on the left side, as you can see, we have two RM cells, NVM cells connected to the crossbar array. This is a word line and this is bit line. Once we add the voltage, apply the voltage on the word line, and this is a resistance of the cell, then the current accumulated here is the voltage divided by the resistance, or the multiplied by the conductance. And the current detected here on the bit line, on the end of the bit line, according to the Kirchhoff's law, it's the current accumulated on the both multiplications. So basically, through the applying voltages on the word line and detect the current on the bit line, we can do such vector multiply vector operations. And once we have consider about the crossbar array that non-volatile memory has, we can do the vector multiply matrix operations in this kind of crossbar array. So let me explain more about this technology using as an example. Here is an example that uses 4x4 non-volatile memory array, and we store the data in the format of resistance in here, and we apply the voltages, as I mentioned before, on the word line, and detect the current on the bit line, and the bit line is equals to the calculation of the vector multiply this vector. So let's consider about how we can map this vector multiply matrix operation in this crossbar NVM-based processing using memory crossbar array. So first of all, we store the matrix in this crossbar array in the format of resistance, and then we convert this input to the voltages and apply them on the word line. At the end of each bit line, we detect the output. Then through this very simple sensing, let's say analog-based computation, we can do a vector multiply matrix operation in nearly a read cycle, which is really fast compared to the traditional ways that we load data to the processing units, compute, and then store back to the memory. We did this computation inside the memory using the memory. And here's more details about how we can use this crossbar-based processing using memory. That we need some peripheral circuits such as digital to analog conversion, and we need to some sample and hold things to hold the signals here. And then we need, for example, the analog to digital conversion at the end of each bit time. Also, we may need some shift and add operation, the peripheral circuits to support more bits. If we, for example, now currently can support each of the NVM cell can support to store cannot store more than 7 bits, and usually we store 4 bits in each cell to make sure that we have the good, let's say, accuracy inside it. So if you want to support more bits, then we need some shift and add circuits to support the computation on more bits. And as you can see here, this part is the analog part that we use to do the computation. It's analog-based computation. And outside is the digital part that we can connect to the existing systems. So here is an example that's how this kind of like processing using memory units can be used efficiently for current applications such as machine learning algorithm. So here is an example that 2D convolution, which is very frequently used in the machine learning applications. And here's the input feature map. And here is the output feature map. And we use the kernels and to multiply the input feature map and get the output. So to enable this kind of computation, we just store, here is an example, we store the kernels of the neural network in the crossbar in such a NVM-based using memory crossbar. And then we take the input streamly and convert them into a vector and then apply it on the this NVM-based beam crossbar. Then we can get the output efficiently. Basically, this is like a kind of a data conversion and mapping to the existing processing using memory unit can be useful. And to support other operations, to support the whole computation of the machine learning applications, we also need some other things such as we need some storage for the intermediate data. We need some peripheral circuits to do other operations such as nonlinear function inside the machine learning applications. So we have a example system here that we have a CPU and DRAM, and we have the NVM-based pin. We use the NVM-based pin to accelerate the modern applications such as machine learning applications. And here we use the processing subarrays, which has the nonlinear function arrays, which is usually the peripheral circuits designed for the functions inside the memory. And we have the NVM-based pin arrays that I explained it before, which is very efficient in the computation of vector matrix multiplication, which can be which is a dominant operation inside the machine learning applications. And also we have some multiplier arrays to support other operations. So here is a paper that we use such kind of NVM based processing using memory technologies, and is used for the bioinformatics application. And I will talk about this paper in detail at the end of this lecture. And here's another paper that we used NVM-based processing using memory arrays to support the base calling in the bioinformatics application. Base calling basically is dominated by it's a machine learning neural network based algorithm, and it's not dominated by the vector multiply matrix operations. So if you're interested, you can take a look at this paper. It's just published maybe several months ago in Micro, maybe only 1 month ago. Yeah. So here are more papers that talk about the processing using memory technologies, such as processing for the convolutional neural network, and for the another one for the neural network. And there's also neuromorphic neural network based. It's like a similar structures that I explained before. So there's some more courses that you can take a look at the historical array and the convolutions used in the machine learning, and you can have a comparison to see what's the benefits of processing using memory, what's the benefits of historical arrays, and what's the benefit of a general, let's say, purpose design. And another interesting thing about emergent memory technology is we can actually consider to merge the memory and the storage. Because before we only talk about how we can replace the memory, the main memory, the DRAM with the NVM, or how we can use a hybrid main memory. But now we can consider another thing is like we merge memory and storage. Only use the pure emergent non-volatile memory, since it serves as a storage at the same time, but it has a higher performance compared to storage. So let's have a look at the current problem in the nowadays system. So we have the HDD, let's say SSD, which is non-volatile, but it's very slow and so it's a block address compared to the other memory space. And the current main memory, which is usually DRAM, it's volatile, it's faster, but it's byte addressable. It's different from the different granularity of from the storage that accessed by byte and accessed by the block. And now we have NVM, non-volatile memories, which combine the characteristics of memory and storage. It's fast and it's byte addressable, and also at the same time it's non-volatile. So then we need to consider about the existing system that we have two-level storage, which is quite complex because we need to use different interfaces between the memory system and the storage system, right? So we have the load, for example, for here to access memory, we have the load store instructions. But for the file system, for the storage, we have file systems such as using the fopen, fread, and write for the. So it's quite complex design for the two-level storage system. So what we want to change now is like if we consider about using two systems on the side, we consider to unify the memory and the system, so we can provide one unified interface. So the goal is to unify memory and storage management in a single unit to eliminate the wasted work to locate, transfer, and translate data at the same time. So to do this, we can improve both energy and performance at the same time, and we also can simplify the program model as well. And here is the persistent memory design that we only have the CPU, and through the interface, we can access the persistent memory. And it provides an opportunity to manipulate the persistent data directly. Here is an example that we have the persistent memory coding here, and use the load store to access the memory manager to access the hardware. And persistent memory use the access and the information to allocate the access, and migrate data, access data in the heterogeneous array of devices. And so it exposes the load and store interface to access the persistent data, and so applications can directly access the persistent memory. There's no conversions between different systems, and there's no translation, and also location overhead for the persistent data. And it manages the data placement, location, and persistence, and the security to get the best of the multiple forms of the storage. Also, it manages metadata, storage, and retrieval, this can be adds a lot of overhead, which need to design well and need to be managed well. But this also provides some benefits, like it also hooks and the interface for system software, make it simplified to enable better data placement and management decisions. So the persistent memory exposes the large persistent address space to the clients, to the programmers, but it may different devices to satisfy this goal. So from fast and low capacity volatile DRAM to slow and high capacity non-volatile HDD flash and other NVM devices in between. So the performance and the benefits can benefit from a good placement of the data among these devices. We need to think about it, as I mentioned before, and to utilize the benefit of each device and avoid their weakness if possible. For example, we can consider two important application characteristics, which is locality and persistence. And for example, here, if we have columns in a column store that scans through only infrequently accessed data, so we can place them on the flash since it has less locality, but it needs some persistence. And another case is that we want to use some frequently updated index for content delivery network. So we can place it in DRAM since it has more data reuse. So it's better to, and also it requires high performance, and it's better to place in the DRAM. So we conclude that applications or system software can provide hints for the data placement. And so let's consider about these three baselines for the persistent memory system. One is the traditional system, that's HDD system, which use the non-volatile DRAM memory and the persistent HDD storage, which cost a lot of overhead for operating system and the file system, and also cost some overhead for the system code and buffering. And another thing that we mentioned before is the NVM baseline. That's it's the same thing as HDD, but we replace the NVM, replace the HDD with NVM, which still has some system overhead since we require these different system software to access the storage and memory. But for the persistent memory, it uses only the NVM to ensure the full system persistence, and all data are using the load and stores, which is a unified software, and that it does not waste time on system calls. And also the data is manipulated directly on the NVM devices. So here is the evaluation of the system compared to the HDD 2 level is a traditional one, and the NVM 2 level, which is replace the HDD with the NVM on the traditional architecture, on the traditional system, and the persistent memory, which is unified the memory and the storage at the same time. So as you can see, it can achieve really good speed up compared to the traditional two-level memory and the storage system. And here is the energy consumption. Also, it can achieve a lot of energy consuming in this kind of unified memory and the storage system. And here's a paper As I mentioned before, there's a big challenge is that we combine the memory and the storage. We need to think about how to use it, and but the solution is we can provide a unified interface to all of the data. So it simplifies the management of the system software, and also it's easier for us to use. And here is a persistent memory module that is the unified memory and the storage. And another example is processing using memory that which can processing inside the DRAM engine to replace the standard DIMMs. And but there's another question, it's like how to ensure the consistency of the system and data if all the memory is persistent. So there's two extremes. One is that we can ask the programmer to do it, which one is ask programmer to do it, and one is ask a system to do it. It's transparent to the programmer. But there are so many options in between these two extremes. So let's have a look at the example of the consistency problem. So for example, here I need to add a node in the linked list. So firstly, I link to the next, and I link to the previous one, and I remove the link between these previous two nodes. And however, let's think of a situation that we have a power down when we link the node to the next, then we lost this data, right? So here causes a problem that system can cache, resulting in an inconsistent memory state. And here there are some solutions to manage the consistency, and there's 3 papers and about manage consistency. Here is the automatic thing to manage the data to ensure the consistency. However, there are some limitations when you adopt this NVM because I have to rewrite the code to clear partitioning between the volatile and non-volatile data. And also it's really a big burden on programmers because you need to carefully think about this data should be volatile or non-volatile. And here is an example code that update the node in the persistent hash table. And let's have a look at this one. So we need to manually declaration the persistent memory components, and also we need a new implementation of this one. And also the third-party code can be inconsistent, and also there are some prohibited operations. So as you can see in these examples, there's a lot of burden for the programmers to use this kind of memory. And here's an approach that we propose. The goal is to use a software transparent consistency in the persistent memory systems. And the key idea is to periodically checkpoint the state and recover the previous checkpoint on crash. This is a new hardware-based checkpointing mechanism that checkpoints as multiple granularities to reduce both the checkpointing latency and the metadata overhead, and also overlaps the checkpointing and execution to reduce the checkpointing latency, and also adapts to DRAM and the NVM characteristics, and performs within 5% of the idealized DRAM with zero cost consistency. So here is an example that overlapping checkpointing and execution. Before it was like this, and after we overlapping the running and the checkpointing, we can save some processing cycles and to benefit to gain some performance benefit here. And okay, here's the paper. We need some programming ease to explore the persistency. And here's another paper here, and another one about the loose ordering consistency for the persistent memory that we don't have very restrict things for as a traditional ones. And also they cause some security and data privacy issues. When we consider non-volatile memory, we store the data inside the memory, and if it's volatile, then when the system is powered off, or when it's the memory is taken by others, it's just a power off. We don't have the data, so it's okay. But let's assume that we consider the situation that we have a persistent memory, have a non-volatile memory here, and someone just take a memory from the system. It can read the data, it can review some information inside the non-volatile memory now. So it caused some security and data privacy issues. So there's the major things here is firstly the endurance problem. As we mentioned before, when we write a lot of data frequently to the non-volatile memory, it can die maybe in several, let's say, days. Because we have a kind of analysis that if we maliciously write the NVM, we can make it wear out in a very short time. So, sorry. The other thing is that the hybrid memory, if we have a hybrid memory system, then you will know that this data is stored in the DRAM or is stored in the NVM by doing some side channel attack, detecting the latency of the access to different memories, and to reveal some information here. This also can be something like the data cannot be removed after power off, as I mentioned before. So you need to consider about the privacy issues in when you use the NVM. And to conclude, so of course, the imagine memory technologies has a lot of benefits regardless of the challenges. So, but it's still in developing technology, and we need to think about a lot of problems when we're using this kind of emergent technology. And it can enable the order of magnitude improvements. Also, it can maybe provide more opportunities for new applications and computing systems. So when we think about it in a holistic way, we have to think across all of the design the systems when we have introduce a new memory technology here. So yeah, so if you still doubt about this emergent technology, you can think about the history that when we have the flash memory, right? It was a really doubtful emerging technology, and for at least 2 years. But flash now is a successful device. So to keep an eye on such kind of like emerging technologies, and think about it, overcome the challenges, and also design let's say the full stack system designs to make sure that we can utilize the benefits of these new emerging technologies. And there's a paper that you can read about the previous history of the solid state drivers, SSDs. Okay, so there are many, as I mentioned before, there's many design and research opportunities in the non-volatile memory, such as the enabling complete persistent memory, computation in or using the NVM memories. Now, hybrid memory systems, we need to consider about the data placement or the migration or the other memory management schemes. Also, there are some security and privacy issues in the persistent memory system. There's also a very hot topic, the security issue. And reliability and endurance related problems, such as malicious endurance-based secure attack. Also, the virtual memory system for NVM, such as the virtual block interface. Okay, so do you have any questions? about this, all of these NVM things. So if you don't have any questions, I will continue to introduce a paper that I've been done on using the non-auto memory to for the genome analysis. Very interesting topic. Okay, then I continue with introducing this paper. It's called GenePip, which is in-memory acceleration of genome analysis via tight integration of base calling and remapping. So let me firstly give an overview of this paper. And genome analysis enables us to determine the order of DNA sequence inside the organism genome. It plays a very important role in the outbreak tracing, personalized medicine, and the understanding of evolution, and so on. However, the modern genome sequencing machines cannot sequence the whole genome, cannot we have input for the DNA sequence. We cannot sequence the whole reference genome. What it does now, the state-of-art, all of the sequencing machines does now is chop the DNA sequence into small pieces, and the small pieces go through the sequencing machines and provide some randomized fragments of the original DNA sequence, which is called as genome reads. It's called as reads in the genome sequencing. And there's a very popular technology called the nanopore sequencing technology. It's a widely used sequencing technology because, as you can see here, it's very small, it's a palm size, and it also provides other available portable sequencing devices. It has high throughput. Also, it's very cheap compared to other sequencing technology. And we found that there's two main limitations in the current genome analysis pipeline for the nanopore-based genome sequencing analysis. So there are multiple steps in the genome analysis, and the first big limitations here is there's a large data movement between multiple steps. And the second limitation is there's a lot of wasted computation done on the data that is later discovered to be useless. So we propose GenePip. GenePip is a fast and energy efficient in-memory acceleration system for the genome analysis pipeline via tight integration of genome analysis steps. GenePip has two key techniques: a trunk-based pipeline, which provides a fine-grained calibration of genome analysis steps, and the early rejection, which timely stops the execution on useless data by predicting which reads will not be useful. And GenePip outperforms the state-of-art software and hardware solutions using CPU, GPU, and optimistic PIM a lot. So I will firstly go through the background and motivation of this paper. And this is the figure about the genome analysis pipeline. First of all, we have the DNA here. We go through the DNA string goes through the nanopore, and it will change. It will change the electrical signals when it goes through the nanopore, and we have the raw signal data here when the chopped DNA sequence goes through it. So after the genome sequencing, we have this kind of pieces represented by the raw signal data, and we store them in the storage. Then we continue with the first step, which is usually the base calling, where we use a neural network to translate the raw signals to the ACGTs, which is usually human readable data. Here we translate one trunk by trunk, since the size of the raw signal can be very long. It varies from like thousands to million bases. So after we translate the raw signals trunk by trunk to the reads, as you can see here, the green one represents the high quality translation, and the red one represents the low quality translation. after we finish translate all of the signals, we store them in the storage. And then continue with the second step, which is usually the read call control. In the read call control, we calculate the average score of the read, quality score of the read. And if the read is, the quality score of a read is lower than a threshold, it means that these kind of reads will not provide some useful information for us when we do the downstream analysis. So we just discard it. And if it's high quality reads, then we store them in the storage and continue with the next step, which is usually the read mapping step inside the genome analysis. And in the read mapping, we compare the reads to the reference genome. If the reads can be mapped to the reference, it cannot be mapped to the reference genome, then we discard it. And if the reads can be mapped to the reference genome, then we store the mapping information and we finish the whole genome sequencing analysis pipeline here, traditional one here. So, okay, then let me talk about more about the two limitations that I mentioned before using the example of a human data set. So at the beginning, we have the raw signals, it's around 4,000 gigabytes. And after base calling, we have the reads transferred more than 500 gigabytes transferred to the next step, which is read call control. And then we have still more than 400 gigabytes transferred to the next computation step, which is read mapping. And then we have the mapped reads stored in the storage. So we conclude that there's a large data movement between genome analysis steps. And the second limitation here is the wasted computation. We still use the human data set to talk a little bit more, continually show the limitation here. For example, after base calling, we have all of the reads, but after the read call control, we only have less than 80% of the reads that are useful. And after the read mapping, we only have less than 70% of reads are useful. So we conclude that there's a considerable amount of computation on useless data due to the low quality reads or the unmapped reads. And let's have a look at what the state-of-art works have been done in this area. So as I mentioned before, NVM-based PIM is very efficient technique to reduce the data movement by processing data using the memory. So there's one work using the NVM-based PIM for the dot production operations, as I introduced in the detail before. For the base calling, since base calling is a neural network-based approach and is mainly use the vector matrix multiplication. And there's another work, so there's some errors here. So using the NVM-based PIM for the search and addition operation and to accelerate the read mapping. And these two approaches reduce the data movement inside a single genome analysis step, only inside the base calling or read mapping. However, it exacerbates the data movement overhead between analysis steps. And we conclude that no prior work tackles the data movement between analysis steps and useless computations. So the goal in this paper is to efficiently accelerate the entire genome analysis pipeline while minimizing the data movement between analysis steps and also reduce the useless computation on the useless data. And so we performed a study to quantify the potential performance benefits, and the results are normalized to performance of GPU. First, we assume that we have the NVM-based PIM accelerators for separate base calling and remapping, where we assume that there's no data movement and there's a lot of on-chip memory spaces to store the intermediate data, which is can achieve 2.7 times speed up. And second, we consider there's no data movement between the accelerators of the analysis steps, which can achieve 6.1 times speed up. And third, we consider there's no data movement and no user reads, which is the ideal case in this scenario, which can achieve 9 times speed up compared to the GPU. So then let me go through the details of GenePip. So GenePip is the first holistic in-memory accelerator for genome analysis pipeline, including base calling, read call control, and read mapping steps. GenePip has 2 key techniques. One is trunk-based pipeline, and one is early rejection. I will firstly introduce the trunk-based pipeline, which enables fine-grained planning of genome analysis steps and processes reads at the trunk granularity, which is usually, let's say, 300 bases. It's a subsequence of a read. And trunk-based pipeline increases the parallelism by overlapping the execution of base calling and read call control and read mapping. Also, trunk-based pipeline reduces the intermediate data by processing the data as soon as the data is generated. And trunk-based pipeline also provides some opportunities for the early rejection by analyzing the read at the trunk granularity. So here is I use reads, which consists of 4 trunks, C1 to C4, to introduce this comparable methodology to the conventional pipeline. So in the conventional pipeline, we base call trunks 1 by 1 and assemble them into a read. And we do the quality control and read mapping on the granularity of a read. And for the trunks-based pipeline, when we base call the trunk, at the same time we base call the second trunk, we do the read call control on the first trunk, and we do the partition computation of read mapping on first trunk. And then at the end, we assemble them and finish the computation of read for the read mapping. And as you can see here, we by overlapping this computation of different steps, we can save a lot of cycles. And the second key technique of GenePip is early rejection, which we stops the execution of useless reads as early as possible by using a small number of chunks to predict the usefulness of a read. And early rejection predicts and eliminates low quality and unmapped reads from the genome analysis pipeline as early as possible. Here is the procedure of early rejection. First of all, we base call a small number of chunks, and then we check the average quality score of these chunks. If it's higher than the threshold, if it's lower than the threshold, then we directly stop the analysis on this read. And if it passes the quality check, then we base call more chunks and map the base call chunks so far to the reference genome and check the mapping score. If it passes the check, if it fails the check, then we stop the analysis on the current read. If it passes the check, then we base call the remaining chunks and execute the remaining computation in the read mapping. So early rejection includes 2 main key techniques: early rejection based on the trunk quality scores and early rejection based on trunk mapping scores. So there are more details in the paper to discuss how we can choose the trunks that we use to predict the quality scores and the trunk mapping scores. So it's worth to mention that CPU and ER can be applied on the different systems such as CPU, GPU, and PIM. And we implement CPU and ER using PIM, since PIM is more efficient to reduce the data movement between genome analysis steps. And also it can provide timely feedback to the early rejection. So we also applied CPU and ER on CPU and GPU baselines, and also some speed up and energy savings. So do you have any questions so far? Then we continue with the implementation of GenePip. So GenePip has 3 modules: the base calling module, the read mapping module, and the GenePip controller. So this kind of GenePip chip is directly connected to the sequencing machine. So it receives the raw signals from the sequencing machine, and then it stores raw signals in the EDRAM in the GenePip controller. And then IEDM forward the signal trunks to the in-memory base caller. As I mentioned before, the in-memory base caller is accelerator processing using memory accelerator designed for the machine learning applications. And it can forward the base coded scores to the pin-based trunk coded score calculation that we designed this in-memory calculation for the trunk coded scores. And then it's forward the base code trunks along with the trunk coded scores to the GenPip controller. And GenPip controller forward the trunk to the read mapping module to do the in-memory read mapping. And it will send the read mapping results to the storage. So basically, here we execute the normal traditional genome analysis pipeline, but in a very in a fine granularity, which is a trunk granularity. And we tightly integrate all of these components to make sure that the data movement on chip is small and it's streamed. So we don't need to store a lot of intermediate data on chip. Also, we consumes the data as soon as the previous step generates the data. And recall that we have early rejection technique. And to enable the early rejection in GenPip, we use the trunk coded scores. We have the design early rejection controller in the GenPip controller. If there's early rejection for the trunk coded scores, based on the trunk coded scores, we send the early rejection signal to the base calling module to terminate the execution of genome analysis on the current read. And to enable the trunk mapping score-based early rejection, we use the trunk mapping scores that from the read mapping module. And if there's early rejection, then we send the signals to both modules to terminate the execution on the current read. So these are the new modules that we designed in the GenPip. And by tightly integrating the genome analysis pipeline, it reduces the data movement and eliminates the useless computation as soon as possible. So do you have any questions so far? Yeah, sure.
Are these different components implemented in hardware?
It's a really good question. So basically, the CP and ER can be purely implemented by the software. But if we consider that we implement by software and execute in the traditional computer architecture, such as CPU-based system, then we still have a lot of like data movement. And when we do the early rejection, we need to, for example, inside each read, we need to read the data. And the latency is higher compared to the when we do inside the processing using memory. So it will waste some time to do the decision of early rejection. So basically, as I mentioned before, this CP and ER can be implemented in the different systems, but the PIM is the most efficient system for the CP and ER. Yeah, is that clear? Oh, thank you. Then if you don't have any other questions, I continue to the evaluation part. So for the GenPip, we evaluate different parts with different simulators that, for example, the OVCM and Cacti, and there's more detailed simulation methodologies in the paper. And the baselines that we use in the presentation, there's 3 baselines, but in the paper, there are more baselines. We compare to different systems, state-of-art systems. So baselines in this presentation is CPU and the GPU and the optimistic PIM, where we assume there's no data movement between steps, and there's intermediate data storage on the chip costs no overhead. And the data sets we use is E. coli and human data sets, which are commonly used in the bioinformatics applications analysis. So here is the performance result of GenePip. GenePip provides 41.6 times speed up of a CPU, 8.4 times speed up of GPU, and 1.4 times speed up of optimistic PIM. And there's more result in the paper showing that both CP and ER are critical to the speed up. And here's the result for the energy efficiency. So GenePip provides 32.8 times energy saving compared to CPU, 20.28 times energy saving compared to GPU, and 1.37 times energy saving compared to the optimistic PIM. And there's more result in the paper showing that early rejection is especially critical to the energy efficiency because CP may overlap some execution time, but the early rejection, they directly reduce energy that we used for analysis those useless data. So here's the paper, and there's some more details inside the paper, include the details of CP and ER. That's how we can sample the trunks from the read, because for the low quality the quality score calculation, we need to sample different let's say the trunks separately, not continuous trunk, because usually the continuous, we found that the continuous trunk, they have a very similar quality scores. So we use a discrete manner to sample the trunks. But for the mapping score, we sample the continuous trunks, since we need close information to do the mapping. And also there's some more detailed GenePip implementation, include the GenePip controller, early rejection implementation, and in-memory seeding accelerator that we, cause we have a different read size, and we need to seed from, take the seed from each read. Then we design a sheet to seeding the seed efficiently to feed it to the processing using memory for the string matching operations. And there are also results of applying trunk-based pipeline and early rejection in the CPU and the GPU. Sorry. So, and also there's some sensitivity analysis on the numbers of sample trunks used for ER, because we require some pre-processing of the data, because there are some different characteristics for different genomes, such as E. coli and human, small, larger genome data set may require more information to when we decide to sample the trunks, and we decide make the final decision that it's useful or not. And we first do the pre-processing analysis to make sure that we won't have accuracy loss, that we reject the wrong data, the wrong reads, let's say. And also we have area and the power analysis in the paper. Okay, do you have any questions? Then I conclude this work. So in this paper, we propose we find a problem that in the current genome analysis pipeline, there's two big limitations. One is there's a large data movement between the analysis steps. And the other thing is there's a lot of useless computation done on the data that is only later to be found that is useless. So the goal is to tightly integrate the genome analysis steps to reduce the data movement between steps, and also eliminate the computation on useless data. And GenePip is the first in-memory genome analysis accelerator that tightly integrates the genome analysis steps. So GenePip has two key techniques. One is trunk-based pipeline, and another one is early rejection technique. And GenPip outperforms the state-of-art software and hardware solutions using CPU, GPU, and optimistic PIM by 41.6 times and 8.4 times and 1.4 times respectively. So, okay, do you have any questions about this paper? Okay, then I think we can finish earlier. That's all about the today's lecture, since we only take a break one. So, or do you have any more questions about the non-volatile memories or processing using non-volatile memories? Quite interesting topic. So if you don't have any questions, then I think we're done for today. Oh.